What if everything we thought we knew about the universe was just wrong? What if the universe wasn't made of tiny particles but tiny vibrating strings? These strings would be so small we can't even see them, yet they could hold the answer to the biggest mystery in physics: how to combine the laws that govern the very large, like gravity, with the laws that govern the very small, quantum mechanics. That's the mind-blowing question at the heart of today's topic. We're diving headfirst into the ultimate physics showdown. String theory versus loop quantum gravity. Get ready for a wild ride because we're about to explore two of the most bizarre and exciting ideas in all of science. These aren't just some abstract theories, they're our best attempts to understand the very fabric of reality. So buckle up because things are about to get strange. In one corner, we have string theory, a heavyweight contender that's been around for decades. String theory suggests that everything in the universe, from the smallest particles to the most massive black holes, is made up of these tiny vibrating strings. Think of a guitar string, but a billion times smaller. Just like different vibrations of a guitar string produce different musical notes, different vibrations of these fundamental strings create all the particles and forces in the universe. In the other corner we have loop quantum gravity, a scrappy challenger looking to shake things up. Loop quantum gravity takes a completely different approach. Instead of focusing on particles, it focuses on the very fabric of spacetime itself. Imagine spacetime as a smooth fabric. Loop quantum gravity says that if you zoom in close enough, you'll see that spacetime is actually made up of tiny, interconnected loops, kind of like a chainmail suit. So, which theory will reign supreme? That's what we're here to find out. Welcome to the mind-boggling world of string theory. Imagine a universe where everything, from the tiniest particles to the most massive black holes, is made up of tiny vibrating strings. These strings are so incredibly small, billions of times smaller than an atom, that they're completely invisible to our most powerful microscopes. But don't let their size fool you. According to string theory, these infinitesimal strings hold the key to understanding the fundamental building blocks of the universe. Just like a guitar string can vibrate at different frequencies to produce different musical notes, these fundamental strings vibrate in different ways to create all the particles and forces we observe in nature. It's a radical departure from the traditional view of particles as point-like objects. In string theory, there are no point-like particles, only these extended one-dimensional strings, and these strings are not made of anything else. They are the most fundamental entities in existence. Now, how do these strings create the universe we see around us? Picture a vast cosmic symphony orchestra, but instead of instruments, we have these tiny, vibrating strings. Each string vibrates at a specific frequency, and these vibrations determine the properties of the particles they create. Some strings vibrate in a way that gives rise to electrons, while others vibrate to create quarks, the particles that make up protons and neutrons. The forces that govern these particles, like electromagnetism and the strong and weak nuclear forces, are also thought to arise from the vibrations of these fundamental strings. It's an incredibly elegant and unified picture of the universe where everything is ultimately made of the same fundamental ingredient: vibrating strings. This concept of unification is one of the most appealing aspects of string theory. It promises to bring together all the forces of nature into a single, elegant framework. One of the biggest mysteries in physics is how to reconcile the two pillars of modern physics: Einstein's theory of general relativity, which describes gravity as the curvature of spacetime, and quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels. These two theories are incredibly successful in their respective domains, but they seem to be fundamentally incompatible with each other. String theory offers a potential solution to this long-standing problem. By replacing point-like particles with extended strings, string theory naturally incorporates gravity into its framework. The way strings interact with each other gives rise to a force that behaves just like gravity on large scales. This unification of gravity with the other fundamental forces is a remarkable achievement of string theory. It's a glimpse of a deeper, more fundamental theory that could potentially explain the universe at its most fundamental level. Here's where things get really weird. For string theory to work mathematically, it requires the existence of extra spatial dimensions beyond the three we experience in our everyday lives: length, width, and height. These extra dimensions, typically 6 or 7 of them, are thought to be curled up and compactified at incredibly small scales, much smaller than even the tiniest subatomic particles. Think of it like a garden hose. From a distance, it looks like a one-dimensional object, but up close, you can see that it has a second dimension, curled up in a circle. Similarly, string theory suggests that our universe may have extra dimensions curled up at scales too small for us to see. The shape and geometry of these extra dimensions are thought to play a crucial role in determining the properties of the universe, such as the types of particles that exist and the strengths of the fundamental forces. One of the biggest challenges facing string theory is the lack of direct experimental evidence. The strings are so incredibly small that it's unclear if we'll ever be able to observe them directly. However, there are indirect ways to test the predictions of string theory. For example, some versions of string theory predict the existence of supersymmetry, a symmetry between fundamental particles that could be detected at particle accelerators like the Large Hadron Collider. Others predict subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang. While no definitive evidence for string theory has been found so far, the search continues. Scientists are constantly pushing the boundaries of experimental physics, hoping to catch a glimpse of these elusive strings or find indirect evidence of their existence. Despite its elegance and potential, string theory is not without its critics. One of the main criticisms is that it's incredibly complex and mathematically challenging, even for seasoned physicists. Another challenge is the so-called landscape problem. String theory allows for a vast number of possible solutions, each corresponding to a different possible universe with different physical laws. This has led some to question whether string theory is truly predictive or simply a framework for describing a multitude of possible universes. Despite these challenges, string theory remains a vibrant and active area of research. It has sparked countless new ideas and insights into the nature of gravity, quantum mechanics, and the very fabric of reality. Whether string theory ultimately proves to be the theory of everything or not, it has undoubtedly enriched our understanding of the universe and will continue to inspire physicists for generations to come. Welcome to the intriguing world of loop quantum gravity, or LQG. Unlike string theory, LQG suggests spacetime is quantized. Imagine spacetime as a fine, interconnected network of loops. These loops form a spin network, the building blocks of spacetime. LQG merges general relativity with quantum mechanics, offering a new perspective on the universe. In classical physics, spacetime is often visualized as a smooth, continuous fabric that can be warped and curved by mass and energy. This visualization works well on large scales, like planets and galaxies. However, loop quantum gravity proposes that if we zoom in far enough, this seemingly smooth fabric reveals its true nature, a complex network of quantized loops. These loops are not just mathematical abstractions, they represent the smallest possible units of space. Think of spacetime as a fabric woven from these microscopic loops, much like a piece of cloth is made from interwoven threads. This new perspective has profound implications for our understanding of gravity and the structure of the universe. By quantizing spacetime, LQG provides a framework where gravity is naturally incorporated into the quantum realm. Instead of treating gravity as a continuous force, it emerges from the interactions of these loops. This allows for a more seamless integration of general relativity and quantum mechanics, something that has eluded physicists for decades. Loop quantum gravity quantizes space into finite, indivisible units called quanta. These quanta are incredibly small, on the order of the Planck length. At this scale, classical geometry breaks down, giving rise to quantum geometry. Quantum geometry replaces the continuous view of space with a discrete structure. Each quantum of space forms a network known as a spin network. These networks evolve into spin foams describing spacetime changes. Spin networks and spin foams are central to the mathematical formulation of loop quantum gravity. A spin network is a graph where each link represents a quantum of area, and each node represents a quantum of volume. These networks are not static, they evolve over time, giving rise to spin foams, which can be thought of as the worldlings of spin networks in four-dimensional spacetime. Spin networks provide a way to visualize how spacetime is quantized. Imagine a three-dimensional grid where each intersection is a node and each line connecting nodes is a link. These networks can exist in various configurations, representing different possible geometries of space. As these networks evolve, they form spin foams, which represent the dynamic nature of spacetime. The concept of spin networks and spin foams allows physicists to calculate how spacetime behaves at quantum scales. This approach offers a glimpse into the microscopic structure of the universe, providing insights into phenomena like black holes and the Big Bang, which are difficult to explain with classical theories. One of the significant challenges facing loop quantum gravity is the lack of direct experimental evidence. However, there are several indirect ways to test its predictions. For example, LQG predicts that spacetime is quantized, which could leave observable imprints on cosmic phenomena. Scientists are looking for these imprints in the cosmic microwave background, CMB, radiation and gravitational waves. Gravitational wave detectors such as LIGO and Virgo have already made groundbreaking discoveries like detecting the collision of black holes. These observations could potentially reveal subtle effects predicted by loop quantum gravity, offering indirect evidence for the theory. Similarly, precise measurements of the CMB could uncover signs of quantum gravitational effects from the early universe. While direct evidence for LQG remains elusive, the ongoing advancements in observational technology hold promise. As we push the boundaries of what we can observe, we may find the fingerprints of quantum spacetime, bringing us closer to understanding the true nature of the universe. Despite its innovative approach, loop quantum gravity faces several challenges and critiques. One major critique is its mathematical complexity. The equations governing spin networks and spin foams are highly intricate, making them difficult to solve and interpret. Additionally, loop quantum gravity has yet to provide a complete, unified description of all fundamental forces, something string theory aims to achieve. Another challenge is the lack of experimental evidence. While loop quantum gravity offers a compelling theoretical framework, its predictions have yet to be confirmed through observations or experiments. This has led some physicists to question its viability as a true theory of quantum gravity. Despite these hurdles, loop quantum gravity has made significant strides in our understanding of the quantum nature of spacetime. It has sparked new ideas and approaches, contributing to the broader effort to unify general relativity and quantum mechanics. Whether it ultimately succeeds or not, loop quantum gravity remains a vital and active area of research, continuing to inspire and challenge the scientific community. At the heart of modern physics lies a profound mystery, the seemingly incompatible worlds of gravity and the quantum realm. Gravity holds planets in orbit and governs the universe, yet it ignores the bizarre rules of the subatomic world. This clash represents a fundamental gap in our understanding. To grasp this challenge, we delve into general relativity and quantum mechanics, exploring their principles and why they resist coexistence. In the grand theater of the cosmos, gravity takes center stage as the director of cosmic motion. Its influence, though seemingly weak on Earth, extends across the vast expanse of the universe, shaping galaxies, igniting stars, and dictating the fate of black holes. Albert Einstein, in his groundbreaking theory of general relativity, unveiled gravity's true nature, not as a force acting at a distance but as the curvature of spacetime itself. Imagine spacetime as a vast, flexible fabric. Massive objects like stars and planets create depressions in this fabric, much like a bowling ball placed on a trampoline. These depressions are what we perceive as gravity. Objects moving through spacetime follow the curves of this fabric, explaining why planets orbit stars and why objects fall to the ground. General relativity has been spectacularly successful in explaining a wide range of gravitational phenomena, from the bending of starlight around massive objects to the existence of gravitational waves, ripples in the fabric of spacetime itself. Yet, despite its triumph on cosmic scales, general relativity stumbles when we enter the realm of the very small, the domain of quantum mechanics. Quantum mechanics governs atoms and subatomic particles. Classical laws break down, replaced by counterintuitive rules. Particles exist in multiple states intertwined in probabilities. Wave-particle duality is a bizarre aspect of quantum mechanics. Electrons behave like waves and particles. The Heisenberg uncertainty principle states position and momentum can't be known precisely. Quantum mechanics' probabilistic nature clashes with general relativity's determinism. The incompatibility between general relativity and quantum mechanics arises from their fundamentally different descriptions of spacetime and matter. General relativity views spacetime as a smooth, continuous fabric, warped and curved by mass and energy. Quantum mechanics describes matter and energy as quantized, existing in discrete packets. This clash is evident in black holes and the early universe. At a black hole's singularity, general relativity breaks down. Similarly, the Big Bang's infinite density challenges both theories. This incompatibility limits our understanding of the universe. Reconciling these theories is one of science's greatest challenges. The search for a unified theory of physics is not merely an academic exercise, it's a profound quest to understand the fundamental nature of reality. Just as the unification of electricity and magnetism in the 19th century revolutionized our understanding of electromagnetism, a unified theory of gravity and quantum mechanics could unlock profound insights into the workings of the universe. Firstly, a unified theory could help us understand the extreme conditions of the early universe, moments after the Big Bang. By combining the principles of general relativity and quantum mechanics, we could potentially develop a theory of quantum gravity that could describe the behavior of matter and energy at these incredibly high densities and temperatures. Secondly, a unified theory could provide a deeper understanding of black holes, those enigmatic objects whose gravitational pull is so strong that not even light can escape. By reconciling the principles of gravity and quantum mechanics, we could potentially unravel the mysteries of what happens at the singularity at the heart of a black hole and how information is encoded within these cosmic behemoths. String theory, a leading contender in the quest to unify gravity with quantum mechanics, takes a radical approach. It replaces point-like particles with tiny one-dimensional objects called strings. These strings, vibrating at different frequencies, are thought to give rise to all the particles and forces in the universe, including gravity. Imagine a guitar string. Depending on how it vibrates, it can produce different musical notes. Similarly, in string theory, the different vibrations of these fundamental strings correspond to different types of particles and forces. One particular vibration mode of these strings is thought to give rise to the graviton, the hypothetical force-carrying particle of gravity. By incorporating gravity into its framework, string theory offers a potential solution to the incompatibility issue. However, this elegance comes at a price. String theory requires the existence of extra-spatial dimensions beyond the three we experience in our everyday lives, and it has yet to produce testable predictions that could confirm or refute its validity. Loop quantum gravity, another promising approach to quantum gravity, takes a different route. Instead of introducing new fundamental objects like strings, LQG focuses on quantizing spacetime itself, the very fabric of the universe. In LQG, spacetime is not smooth and continuous but composed of tiny, indivisible chunks like pixels on a computer screen. These fundamental building blocks of spacetime are often visualized as interconnected loops, forming a network that resembles a chainmail suit. These loops are not made of anything else, they are the fundamental constituents of spacetime itself. The way these loops connect and interact with each other is thought to give rise to the force of gravity. LQG offers a compelling picture of quantum gravity, one that naturally incorporates the principles of both general relativity and quantum mechanics. However, like string theory, LQG faces significant challenges, including its mathematical complexity and the lack of experimental evidence to support its predictions. The search for a unified theory of physics is still ongoing. Both string theory and loop quantum gravity, despite their promise and elegance, remain incomplete and face significant theoretical and experimental challenges. However, the pursuit of this grand unification continues to drive some of the most exciting and innovative research in physics. New theoretical frameworks, such as causal dynamical triangulation and asymptotic safety, are being explored, each offering unique perspectives on the nature of quantum gravity. Experimental efforts are also underway, searching for subtle quantum gravitational effects in the cosmic microwave background radiation, gravitational waves, and high-energy particle collisions. The quest to unify gravity and quantum mechanics is not merely about finding a single equation that explains everything. It's about pushing the boundaries of human knowledge, exploring the deepest mysteries of the universe, and seeking a deeper understanding of the fundamental nature of reality itself. The pursuit of quantum gravity is an ongoing journey, a testament to the human spirit's insatiable curiosity and relentless pursuit of knowledge. While a definitive theory of quantum gravity remains elusive, the journey itself has already yielded profound insights into the workings of the universe. String theory, with its extra dimensions and vibrating strings, has revolutionized our understanding of the fundamental constituents of matter and forces. Loop quantum gravity, with its quantized space-time and interconnected loops, has provided a new perspective on the very fabric of reality. The future of quantum gravity is bright with possibilities. New theoretical breakthroughs, combined with increasingly sophisticated experiments, hold the promise of unraveling the mysteries of black holes, the Big Bang, and the fundamental nature of space and time. The quest to unify gravity and quantum mechanics is not just a scientific endeavor, it's a testament to the human spirit's enduring quest to comprehend the universe and our place within it. In theoretical physics, string theory and loop quantum gravity aim to unify general relativity and quantum mechanics. These theories take radically different approaches, each with unique strengths and implications. Imagine two master chefs creating the ultimate culinary masterpiece. One chef, like string theory, uses exotic ingredients to create intricate flavors. The other, like LQG, focuses on fundamental techniques to transform simple ingredients. Similarly, string theory and LQG take contrasting routes to quantum gravity. String theory posits the universe is made of tiny, one-dimensional objects called strings. These strings vibrate at different frequencies, each mode corresponding to a different particle. LQG focuses on the quantization of spacetime itself, composed of tiny, indivisible units. These loops are the fundamental constituents of spacetime. This difference has profound implications for unifying gravity with quantum mechanics. The nature of spacetime itself is another key point of divergence between string theory and loop quantum gravity, or LQG. General relativity, Einstein's theory of gravity, describes spacetime as a smooth, continuous fabric that can be warped and curved by the presence of mass and energy. This curvature of spacetime is what we perceive as gravity. Objects moving through spacetime follow the curves of this fabric, explaining why planets orbit stars and why objects fall to the ground. LQG, in stark contrast, proposes that spacetime is not smooth and continuous but fundamentally discrete, composed of tiny, indivisible units like pixels on a computer screen or grains of sand on a beach. These fundamental units of spacetime, often visualized as interconnected loops, form a network that is constantly evolving and interacting. This quantization of spacetime has profound implications for our understanding of gravity. In LQG, gravity is not a force acting at a distance, but an emergent property of the interactions between these fundamental loops. The curvature of spacetime, as described by general relativity, is thought to arise from the collective behavior of a vast number of these loops. Despite their different approaches, both string theory and LQG share the same ultimate goal: to unify all the fundamental forces of nature. Physicists describe the universe using two separate theories: general relativity and quantum mechanics. This division is a source of much frustration and intellectual curiosity. A unified theory would explain matter and energy at all scales. One of the most intriguing aspects of string theory is its requirement for extra spatial dimensions beyond the three we experience. Physicists propose the universe may have 6 or 7 additional dimensions, hidden at incredibly small scales. Imagine a garden hose. From a distance, it appears as a one-dimensional object. Upon closer inspection, it has a second dimension, curled up in a circle. String theory suggests our universe may have extra dimensions curled up similarly, too small to detect directly. One of the biggest challenges facing both string theory and loop quantum gravity is the lack of direct experimental evidence. Both theories operate at energy scales far beyond the reach of current particle accelerators, making it, well, difficult to test their predictions directly. However, physicists are actively searching for indirect evidence that could support or refute these theories. String theory, for example, predicts the existence of supersymmetry, a symmetry between fundamental particles that could manifest as new particles at energies accessible by the Large Hadron Collider. The discovery of supersymmetric particles would be a major boost for string theory, providing indirect evidence for its validity. Loop quantum gravity, on the other hand, predicts that spacetime itself has a granular structure quantized at the Planck scale, which is about 10 to the minus 35th meters. This granularity could potentially manifest as subtle variations in the cosmic microwave background radiation, the afterglow of the Big Bang. Precise measurements of the CMB could reveal these variations, providing indirect evidence for the quantization of spacetime. Both string theory and loop quantum gravity have unique strengths and weaknesses. String theory unifies fundamental forces but requires extra dimensions. Loop quantum gravity quantizes spacetime without extra dimensions. Both theories push the boundaries of human knowledge. The search for a unified theory of physics is an ongoing journey. While string theory and loop quantum gravity have made strides, a definitive theory remains elusive. The future is bright with collaboration and innovation. New frameworks inspired by both theories are emerging. Experimentalists are developing sophisticated instruments to probe quantum gravitational effects. The quest is about expanding human knowledge and exploring the universe's deepest mysteries. So, there you have it, folks, the ultimate physics showdown: string theory versus loop quantum gravity. We've journeyed deep into the quantum realm, exploring these two mind-blowing attempts to explain the universe at its most fundamental level. Both theories offer elegant and compelling visions of reality, but they also come with their own sets of challenges and unanswered questions. String theory, with its vibrating strings and extra dimensions, offers a seductive vision of a unified universe, where all forces and particles emerge from a single, elegant framework. Loop quantum gravity, on the other hand, dives headfirst into the quantum nature of space and time itself, picturing the fabric of reality as a network of interconnected loops. Which theory will ultimately reign supreme? The truth is, we don't know yet. Both theories are still under development, and physicists are working tirelessly to find experimental evidence to support or refute them. It's a thrilling time to be a physics enthusiast because we're on the verge of potentially groundbreaking discoveries that could revolutionize our understanding of the universe. We hope you enjoyed this epic journey into the heart of quantum gravity. It's a topic that pushes the boundaries of human imagination and reminds us of the vast mysteries that the universe still holds. If you're as fascinated by these mind-blowing concepts as we are, then be sure to hit that subscribe button and join us on Time Pilgrimage as we continue to explore the wonders of the cosmos. We'd love to hear your thoughts on this ultimate physics showdown. Do you have a favorite theory? What questions do you still have about string theory, loop quantum gravity, or the quest to unify physics? Share your insights and let's keep the conversation going in the comments section below. Thank you for watching Time Pilgrimage, and as always, please remember to subscribe and like. If there is a topic that you would like to explore, please drop a comment. Until next time, keep questioning, keep exploring, and keep looking up at the stars.